All right. So we are live, and you all can see my screen. You can see me. The screen is coming up. Hi, Sri Lakshmi. Hi, Mohan. Hi, Krishna. So, welcome to the live session, day 2 of learning how to fine tune a large language model, right? So, yesterday was a lot about how transformers are and why it's a big deal to understand transformers, how they work, especially the attention mechanism, especially the query key value thing, right? Because that's really important. Now we are here. We have established on day 1, we have established how these things work. We know what is an encoder. It encodes the incoming text into an enriched matrix which contains a lot of context, the relationship, semantic meanings, and a lot of things into it, right? And this enriched matrix is then decoded by the decoder to produce the output, right? So that's the logic, and it allows or it unlocks parallel computation. And we saw that such vast amount of matrices are taken into picture. Yes, hello Manish, hello everyone, good evening to the session, right? So let us now understand the fact that how do you train okay, sir, can you just brief about gamma in its detail? Yes, today is all about that. Today we will be doing that, right? For sure. Okay, so let us just first take one small recap on how a machine learning model learns. Okay, so input layer, what is the role of input layer? The role is to take the input of the data, okay, whatever the incoming data is, whatever it is supposed to take. Hidden layers are designed to extract patterns, recognize features, recognize things through which they can learn from the data and design rules, their own rules to maybe do some prediction or estimate or predict something, right? Output layer has just maybe a softmax function or maybe an activation function to just give the output to you, right? Initially, what happens is that say we are training a model to learn difference between a cat, dog, and a horse or a mouse. Okay, cat, dog, and a mouse. So we randomly give the picture to the model. The model through its input layers will try to find different features. Like it will try to look into different pixels of the image. Maybe one of the hidden layer will try to find boundaries. One hidden layer will try to find maybe regions. Another hidden layer will try to find more depth, more details, some more complex structures, and then give an output. It will randomly say, maybe I give it a photo of a cat, it will randomly say that it's a dog. Okay, and this is very randomly because initially training starts like this. There's complete random weights initialization, right? We completely that's the majority, in the majority of the cases, the normal or the generic approaches, you start with the random weights, and you let the model give an output. Now based on the output, you will give an instruction back which is in the backward propagation. Now on the output you will say that, hey, this is not at all a dog, it is supposed to be a cat. Then the model will go back. It will now try to change the weights. Okay, maybe it will try to go to the left, maybe it will try to go to the right, say increasing the weight, left say decreasing the weight numbers. Okay, and then retry to predict whether it was a cat, dog, or a mouse. And again it will see, okay, I did mistake, but this time it will again take a feedback that well, this is not exactly the correct output, but you are better than before. So this is how model will keep on with the feedback loop, like the backward loop. It will keep on doing forward iterations, backward iterations, forward and backward iterations to finally adjust the weights to a level that now they are very well trained to detect a cat, dog, or a mouse. So similarly, we understand that any large language model is also trained the same way. Transformers have input and output. In between, there is encoder decoder with the attention mechanisms, and each of them have their weights. Each of them have their own vectors to look into and to train from. Okay, but this is not a joke, right? To train a model, which we realize that it can take crores of rupees to train such a model. So fine tuning, now as a concept, what is fine tuning? Okay, so fine tuning is a task where, suppose there were 10 hidden layers, okay, in any model. In our transformers there are many more layers, right? I told you, like, there could be many layers. So rather than say, for an example, I've trained a model to predict a cat and a dog and a mouse for me now. Okay. Tomorrow I want to train it to predict even horse or a donkey. Okay. So the idea is that all of these are animal. They have different kind of fur, they have eyes, they have legs, they have body. So somewhere we believe that a general model might have learned us to recognize some features which might be useful here also. Okay, so fine tuning is a task when we pick a base model which is good at something. Okay, and then we adapt that model to learn something which is similar to what it is good at something. Okay, so maybe now we can start training a model to recognize a horse for us using its pre-trained weights. So understand the concept. When we are training a model from scratch, we start initializing random weights and then we train the model. Okay, and then we at the end we get a trained model with tuned weights. Okay, so in machine learning, in any model, the 99.99% importance are of weights, these numbers. Okay, once you have these weights with you, you have a model. Models are directly converting into weights. Okay, so there are weights and biases. That's the only thing that a model is all about. So in fine tuning, we do not use random weights. We use the weights which were there in a base trained model, and on top of it we freeze almost initial few layers. Okay, at least there are 10 layers in a model. For an example, we could freeze 5, 6, 7 layers to begin with. Okay, because initial layers, they are all about recognizing maybe the color, the boundaries where this animal is supposed to be, eyes, nose, and things like that, which are common, and maybe these layers will work. The magic will happen, the final decision making will happen in the last few layers, which is where we adapt them again. We only train weights on these weights, which is of course a lightweight computation now, right? Imagine for a forward propagation, if it has to multiply at each of the level and update it at each of the level, then there are 10 iterations to update. In fine tuning, since we are freezing first 7 layers, only last 3 layers are to be updated. So mathematically it is much lesser computation. It is much lesser computation, because of which it is easier to train and fine tune and adapt quickly. Okay, fine tuning in terms of latency is also better because it trains, it converges quickly. So in and it maybe it requires lesser data. So for an example, if I used 100 images of horses and mules and other animals which are similar, zebras, to train the model, and now only have 15-20 images of donkeys, but I can fine tune it because model already has certain similarities with these animals. Okay, so that's also fine. It is quicker, it is convenient, it is cheaper. So that's the reason to use fine tuning. And again, on this behalf of large language models, even a simple task like fine tuning is a headache. Okay, I already took you to that aspect that you might require hundreds of GB to even fine tune something, which is where concepts like parameter efficient fine tuning came into picture. So the agenda of this 3 days boot camp is to emphasize, is to explain what PEFT is all about, parameter efficient fine tuning. Okay, what this concept is all about, this is the idea, and we are dwelling into it now. Okay, like we are not just dwelling, we are diving into it actually. Okay, so the agenda of today would be, we will take an overview of PEFT. We will talk about few key methods in PEFT, what are the applications of PEFT, and we will not just do conclusions. We will start with our coding also today. We did some minor coding yesterday, which was to learn how query key values might work, just to mimic them. Today we will look at the Gemma's architecture. Today we will load it. Today we will play around a little bit of the code. I'll explain you. Okay. Mickey is asking, can we fine tune and run on our normal laptops? No, not at all. That's completely not possible. Even for a laptop which is Windows based, for around 2.5 lakh, it is difficult. About 2.5 lakhs, you might get 4090 laptops with 2,60,000, 2,80,000, 3 lakh budget. On those laptops, maybe you can think about fine tuning something. Okay, but the cheapest thing that you can get to train on your local laptop would be a MacBook, which would cost around 2 lakhs for a 36 GB GPU and RAM variant. Okay, they have a common network. But if you're asking me that how then we are supposed to do it, we are doing it in Google Collab. Okay, Google Collab provides you certain free sets of GPUs available on the internet, which will mimic your 2.5 lakh of setup. Okay, a 16 GB VRAM. All right. So moving ahead, let us take the overview of PEFT, what it is supposed to do. So importance of PEFT is that, first of all, it reduces resources. It drastically reduces resources, and therefore it challenges the fine tuning in a way that it makes it easier. A full fine tuning is very difficult, not at all possible. Forget local machines, even normal servers can't provide that infrastructure to do it. So that's where PEFT will benefit. And see, that's the main idea. Okay, the model will converge quickly, it will adapt to your task quickly with lower memory. Okay, so let us talk about few key PEFT methods. Even before we go there, I'll just go to APXL. So APXML is a site where you can check few things. Okay, so for an example, I'll take a very simple let me take llama for an example. Say I'll take a smaller llama 8 billion model. Okay, so suppose if you have to do fine tuning of this model, llama 8 billion, and if you're supposed to do it for full precision, you can see we need 106 GB free RAM available with us. Okay, so that's not quite possible. Even at the lowest settings, these settings, we are not even bothering about it. So now let us see how maybe PEFT can help. So suppose if we take LoRa for an example, do you see this significant reduction? 106 GB reduces to 18 GB. Okay, and this is a significant reduction, almost you can say 80% plus reduction, just by using LoRa, even at a rank of 16. Even if you go for 32, it's still not challenging. It will still fit in the 18 GB configuration. And if you go for QLoRa, you will realize that even a simple 8 GB GPU can now fine tune this model, right? So that's the benefit, and that's what we are trying to present you when we say how PEFT is beneficial. It reduces computational cost extremely. Now we will talk about few key PEFT methods. The first one being adapter module. This is highly useful. Okay. Yes. So can we fine tune and run on our local laptops? Okay. Yeah. I think there are no more doubts coming in. Let me check if my live chat is working correctly. Let me switch to all chats. Okay. Yes. Okay. We are doing good. Right. So well, adapter modules, what they are. Okay, so suppose if we have an architecture, I'll take an example of a vacuum cleaner. I'm not sure if this is a good example, but we might know what a vacuum cleaner is. I think we all might know what a vacuum cleaner is. So by default, it has a machine which sucks. Okay, there's a suction machine, and there are different you can say adapters to it. One is used to do suction between the sofa seats. Okay, some edgy corners. One is used to do suction on carpets, one is used to do suction on general area. So there are adapters which are available, right? So the logic of adapters is same. We will not change our machine. We will not change how the machine is designed. So in our case, our machine is the large language model. Our large language model was trained, the encoder, decoders, and the positional encoders and the attention layers, they were all trained. They have their own set of biases and weights. Okay, we will not touch it. What we will do is, but on these layers, we will target few layers and add adapters on it. Okay, which will then do the custom adaptation which we want. So those are known as adapter modules, and one of the adapter modules is LoRa, or also known as low rank adaptation. Okay, so how does low rank adaptation works is it works on the principle of breaking bigger metrics into smaller metrics. Okay, so in mathematics there are different ways to do it. SVD, singular value decomposition, is a technique in mathematics. If you are into advanced matrices, you will realize SVD, and there are many more like LU is also a mathematical technique which can help you break down a matrix into two different parts. So if you know how dot product of matrix works, like m cross n into n cross m, if if you if you are multiplying this matrix, you will get the output as first row and next column. That will be the size of the new output. If you understand this, you will realize that a single matrix can be broken down into two smaller matrices. Now, why is this important? The entire heart of the, or you can say the center of gravity, or the crux of the entire agenda of having the PEFT is that by default, large language models are very complex and their matrices are really huge, like 5 and 12 dimensions in a single vector. So if you can break it down into maybe like 20 and 20 wala small you can say metrics, still better, okay, to just use small metrics and then to generate an answer on top of it. Okay, now I could have taken separately 35-45 minutes to just explain you the concept of how these metrics are broken, or how does low rank adaptations metrics breaking works, how they add some you can say maybe they decompose not correctly, and how there's some error which can come up while this decomposition also. But we will not touch the mathematics part, because we will drain all our 1 hour that we have for us with now, and we will not be able to proceed. So I'll give that as a thought of food to you, that maybe you can try to learn on your own that how does the concept of breaking this matrix works, and then regenerating the matrix out of it. Okay, but that's how low rank adaptation works. Okay, so basically when we talk about this, so let us say we focus on a very simple LLM like we took over here. Okay, so Llama 3.1. okay, and even such a model, forget that it takes 105 GB to fine tune. Let us check about inference. What about inference? So if I'm loading Llama 3.18 billion on full precision, okay, like the original model, the way it is supposed to be, it shows 35.46 GB over here, but it can take around 33-34 GB. But you can see that we are focusing on an 8 billion parameter model, even though this is smaller in some context, but still it is big enough. You can say in a family of giants, if we have a small giant, it doesn't mean that it is small. It is still a giant, but a small giant. So even for us, like people, like normal people who are wondering, even we cannot still imagine Llama 3.1 32 GB just to store the weights. 8 billion weights in this model. Just to store these weights, we can load it on RAM. We need at least 36 GB of free RAM to just load it, even if you're doing it on CPU. Forget GPU. CPU पे भी कर रहे हो, RAM के साथ कर रहे हो, we need this much amount of RAM, okay, just to load it. So that's the idea. So Llama 3.1's architecture, it basically consists of 32 groups of modules, okay, stacked onto each other, and the others are called Llama decoder layers. So you can realize how complex this network is, right? So they take up this amount of time. So what the idea is that let us go back to our presentation. So we have LoRa. Okay, so what LoRa does is that it basically breaks down all the weights into smaller composable matrices. We can call it LoRa and LoRa B. Okay, so for mathematical reasons, we can call it, there are two different metrics that come into picture, LoRa A and LoRa B. Okay, so what is the big idea around here is that, one, we freeze the main model, so complete model is frozen. I just told you about how fine tuning works. Maybe in fine tuning we freeze first few layers, we do not change it, only we adapt the last few layers, right? In this type of parameter efficient fine tuning LoRa, we completely freeze the entire main model. What is the benefit of it? We preserve the main model as it is. Okay, we do not tinker with it. We do not change any parameter here and there. We just simply introduce small trainable adapters. I told you this is an adapter type of technique. So we add tiny matrices, like lower rank matrices we call them, and when we fine tune, we do not change the weights of the entire model. We just tune these small matrices. Okay, and since they are working with a dot product, so while when we have fine tuned it, the final answer जो model देगा, the model will take input, convert it into encodings, run through our attention layers. In the attention layers, these small matrices that we introduce, they will be now interacting with the main matrice to do multiplication and then maybe adapt to our use case. Okay, so these adapters are applied to specific target modules. Okay, like I told you, there could be 32, 64, 50 different layers. So we do not simply target them on each layer, because the idea is to keep it simple. Okay, we so I'll say 99% of the 99.99% of the cases, or in general, mostly we will target attention layers only, because these are the decision making layers. So we will apply this small matrices decomposition on the attention layers. We will apply them, and then this is called low rank adaptation. Okay, so why do we call it adaptation? Because we are adapting the new model to now work with this small matrices also to do prediction. Okay, so again, you can see the applications are that they are useful to train models like GPT-3, T5, or anything. I'll give you one interesting insight over here, is that LoRa is not specific to large language models only. Techniques like low rank adaptations can be applied to any deep learning model. The reason we don't need it to apply for the regular deep learning models is because they are self capable. Like the GPUs in normal laptops are also capable to train these models and handle all those layers. We need such techniques mostly when the models are vast, something like a transformer. Flan T5 or T5 are the transformer architectures from Google, which are also like BERT is one example, which is a transformer encoder based model. GPT-3, like OpenAI has launched it. Okay, so these models, they work around on low rank adaptation because it is suitable. This technique is suitable to be applied on any deep learning model which is complex and vast. Okay, so I hope the things are getting clear to you. We are able to understand this part. Okay, now let us proceed ahead. Let us talk about few other techniques. Okay, so weight decomposition, also known as DORA, weight decomposition low rank adaptation. This is one more type of low rank adaptation only. Okay, remember, low rank adaptation kya karta hai? It breaks down the bigger matrix into two small matrix, and then only adapt these two small matrix. Okay, and doesn't touch the entire model. It only fits on some layers that we choose. Okay, I'll show you in code. We will do everything in code. We will choose these layers also manually. We will see the architecture of the model we are choosing and where we'll be applying it. I'll show you everything. Okay, so how is DORA different? So see, if you understand in mathematics the concept of vectors, what are scalar products and vector products, like what are scalar values and vector values, you will realize that vector values are something which have direction as well as magnitude. Okay, so DORA simply decomposes the matrices on the level of magnitude alag or direction alag, and this is much more similar to how actual fine tuning works. Okay, actual fine tuning impacts both magnitudes and vectors, which LoRa also does, but this is the idea of how DORA should work. Okay, so see, DORA enhances cross-domain learning. Okay, so this method reduces computational overhead. It maintains performance because the paper publishes it, but it is one another way if you do not want to do LoRa in any of the case. Okay, so another task is known as prefix tuning. Again, prefix tuning is an adapter method. What happens is that we design small matrices, like these are again some weights. Okay, like prefix weights. Now these weights are trained or tuned. Again, the complete model is frozen. These smaller matrices are trained and tuned on our use case, and we fit them as per like before passing it to the attention layer. We will add this prefix like an adapter to before the first layer and prefix to second layer, something like that, right? So prefix tuning enhances text generation capabilities. Okay, allowing model to generate outputs based on specific prompts, enabling tailored response. Suppose I want to create an avatar. Like we have so many popular avatars in movies, right? Like we have the classical old era Bollywood avatars could be Mogambo. Okay, then maybe then we might have so many different characters we might admire who have certain character. Like we could have Guddu Bhaiya from what was that series? I forgot the name, but people can comment it if I'm getting it right. Okay, and then we could have Pankaj Tripathi playing over there. Okay, we could have Kalin Bhaiya, and similarly there are so many different roles that are there. Okay, so maybe I want to create a chatbot which talks like, behaves like, thinks like, acts like maybe a character I wanted to work. Okay, so in such cases we could do prefix tuning, which will help the model train in a way that it adapts to the language, the nuances, or the vocabulary, or the way the person is speaking. It will adapt to it. So such type of trainings can also be used with prefix tuning. Okay, so that is one more way to look at it. Well, one more way, which is known as again a parameter efficient fine tuning, is prompt tuning. Now, this is something that you all might be already aware. There are so many different ways to prompt: a single shot, multi shot, few shot, chain of thoughts, tree of thoughts. Okay, and so many different ways to prompt. And in itself, how to prompt to a model is a complete 55 minutes to 2 hours of session is enough to learn how to do better prompts. So prompts are nothing but an added set of instruction, which is again coming in free natural language. Like we talk to the model just the way we will talk to any human, and we will tell the model that, hey, you are supposed to behave like some character, say Mogambo from Bollywood series, and you have to talk as per their theme. Your users are this, and you're guiding the model in a prompt and way that the model will try to adapt to it. Okay, so whenever you will give a question to the model, with the question you will also attach this prompt, so that the model knows how to respond. Okay, this is the most simplest form of fine tuning, I will say. It involves zero efforts. Okay, uh, you just need to add a prompt which is less than kbs, or just in kbs of not even an MB to impact the usage or inference or complexity. It is the most simplest and the first thing. So as a doctor of LLMs, what your goal should be, let me tell you that suppose whenever you take up a project which involves working with large language models, and the goal is to adapt the LLM to the use case, so the very first thing that you should apply is prompt tuning. Okay, make sure that you have maximized the performance by prompt tuning. Okay, this is the step one you should do. At least 50-60% improvement you will be able to see just by prompt tuning itself. It can go up to 70% also if you are really prompting it well and you've chosen the model correctly. So choosing your base model is also very important. Okay, so for an example, if you are going to do a drag race, or if you're going to do maybe an F1 race, or maybe if you're going to do race of mileage, or maybe if you're going to do a race of 0 to 100, so choosing your base car is very important here, right? Like for drag setup, you need different kind of wheelbase, different type of wheel sets. For mileage race, you need a different type of parameters. Your engine should be efficient more here, producing less power but more efficiency. For going for maybe a 0 to 100, you do not bother about the efficiency, you bother about the complete robustness, right? So similarly, in case of our programming, whether the task is to solve complex things, do coding, just generate essays, or do summary, do translation, depending on what task it is, we have to choose the base model correctly. How much bigger we will not, we will suffice with a 3 billion model, 8 billion model, 16, 20, 30. Again, a choice of how bigger the model would be, how complex the task would be. If you have chosen the base model correctly, on top of it, then you can go for competitors, right? So in 8 billion market, you can go for Mistral, you can go for Llama, you can go for Quen, you can go for Gemma. So many models on the leaderboard. Okay, so again, this will be a good time to let you know that one more pro tip would be that you should always make sure that you follow LLM leaderboard before doing anything. So Vellum and LLM Stats both are good websites uh, to find the leaderboard. Okay, so on the leaderboard, there's a live benchmark which is updated daily. You will realize that these are the people who are running the race. And let's scroll down a little bit. Over here, you will be able to filter out certain things. First of all, organization, it is fine. Model, it is fine. What if you are simply looking at open source models only? The client requirement is that, hey, we will do this project, but I am not willing to invest in any third party LLM. in this case, you're considered an open source only. What if client is saying that I'm okay to use third-party LLMs, but performance is important? Then maybe you'll go for proprietary. But if you keep it open, we will be able to realize that there are different type of results over here: GPQA, MMLU. Okay, so if you hover over it, you will realize that GPQA is a graduate level Google Proof benchmark. Okay, a benchmark which will decide whether you are able to solve graduate level programming challenges. MMLU is a benchmark which is useful for a wide range of language tasks. Okay, so these are the ratings. Maybe you need a project which involves wide range of language tasks, so you will rate based on something like that. So DeepSeek is a leaderboard at this point, at least on 8th July 2025. Nothing beats DeepSeek 0528 and 0324 model, which is a crazy amount of model, like 670 billion. Have you even heard something like that? Well, I think if you check Llama 4, which is the latest edition, the Llama Maverick, Llama Scout, and Llama Behemoth, these are now groundbreaking behemoths. Well, the name itself is Behemoth. You can see the capabilities. If you view what Behemoth is supposed to do, okay, so you will realize that it has 288 billion parameters and 2 trillion total parameters. Okay, so this is crazy. 400 billion, 109 billion. These are not at all possible. I'm not able to imagine how you will run these models. Okay, but so 671 billion is something that exists. There are models in trillions of weights also. But again, if this is your task, maybe you can realize, okay, these are too much for me, which is very well realized that there is 5.4 reasoning plus, which is relatively a smaller model, comes with a smaller context window, of course. But if you scroll down a little bit, you will realize that, okay, hey, I have Gemini 2.0 Flash also, which is good, and Claude is also doing good over here. So again, a good practice is people that we should always make sure that we check the LLM stats. So Google Gemini 2.5 Pro, I have used this model personally a lot, and trust me, this is really a good model compared to what Grok and OpenAI are charging you. Gemini 2.5 Pro is relatively cheaper and much better. At least it is comparable to flagship level models. Not that the Grok and OpenAI are losing the race, I'll say, but I prefer Gemini 2.4. Like, this is my personal favorite model. And when it comes to quick things, Gemini 2.5 Flash or 2.0 Flash are the best models that I use in my many of the projects. Of course, I'm using GPT. I have used GPT 4.5 recently. I have used GPT 4.1. These are also good, but they are expensive for some of my use cases, right? So again, the idea is that if you pick the LLM correct from here, and if you have chosen your PEFT correctly, which is first do prompt tuning, maybe then go for something like low rank adaptation and move ahead, then that's the step. Okay, because I'm telling you, many of your use cases will not even require fine tuning. Fine tuning is more needed when you have some more big data and you're willing to go with it, right? Now, let's talk about one more PEF technique, which is known as bitfit, also called as bias term fine tuning. So bias term fine tuning, it focuses only on the bias terms. So remember, even for a very simple model like linear regression, y is equals to mx plus c, there is a single weight m and a single bias x. Okay, so similarly, there are many biases and many weights in a deep learning network. So it doesn't bother about training or fine tuning your weight. It completely freezes it. It just uses the bias terms. It just trains and changes the values of bias levels. Well, this is an interesting technique to look at, but not very effective, I would say. But again, it is very quick. Changing biases is not at all a heavy lifting task. So compared to other PEF techniques that I've discussed now, this will be yet the most optimal and the most quick way to do. But again, it has limitations regarding if you are trying to train a complex task using bitfit. It is not a technique designed for it, right? It is designed for maybe if your model is performing some optimal on a task, maybe you can enrich it by using a bit fit PEF training and see whether the model works over there, right? But this is a very lightweight kind of tuning. So heavy lifting is done mostly by LoRa, which is why it is important and it is most popular, and the reason we are looking into LoRa in depth. Okay. After this, there is again one more technique known as IA3 or infuse adapters by inhibiting and amplifying inner activations. So as the name is quite heavy, but in it carries amplifying inner activation. So what does it mean is that this type of PEF training has a very novel approach. It adapts and trains or fine tunes the adaptation layers, okay, by amplifying them. Okay, it creates small matrices which are then applied into dot product to amplify the behavior of different layers, and that's how it's worked. So again, its application is in text classification, so it effectively enhances the classification abilities. So if you are planning to do a project which involves text classification, like maybe this is a legal document, maybe this is like a compliance document, or this is a knowledge based document, or this is some other type of document. Okay, so document classifications, if you're trying to fine tune something, it's better to try this type of paper to apply. Okay, but again, the leader being LoRa is quite applicable everywhere. Okay, LoRa enables efficient training on multiple various tasks. Okay, which includes NLP in general. So these are few different techniques that I wanted to talk about. I wanted to let you know. Now, common use cases, well, we can skip this slide. I already explained you that maybe translation and anything like summarization, classification, they are useful, and we can move ahead with challenges. Okay, so the very first challenge would be the performance compatibility with full training. So just think of it like this, okay, that if I am buying a hotel for my vacation at 1 lakh rupees per night, and if I'm buying a hotel at 30,000 rupees per night, depending upon the perspective, let us say we are middle class. So even for middle class, 30,000 hotel will not seem bad in India itself. Okay, it will not feel bad. It will be really a good hotel. But again, if you compare it to a 1 lakh rupees per night hotel, definitely, like this is my bet, there will be some differences that maybe for a middle class won't matter, but there will be some differences. There logically there has to be some differences because of which it the second hotel costs 70,000 cheaper, and maybe for middle class I can also find a hotel for 3-4,000 per night and will be bang for buck. I'll be satisfied saving 95,000 and not paying for that 1 lakh hotel, right? So same logic if you apply here. See, the original meaning of fine tuning is supposed to be that you completely tune your weights and biases. You completely change these things in the layers, okay, only to get the best performance. Okay, so and even on top of fine tuning is full tuning. So forget full tuning. The idea of fine tuning is like this, okay. So if you are now cheating into fine tuning, if you're trying to find hacks how to fine tune with some hacks, okay, obviously you cannot compare it to the performance of the original logic of fine tuning, right? But here is the catch: the difference is so suboptimal that it doesn't bother many people, right? Why would I pay lakhs of rupees to fine tune something and get 99% accuracy if I can fine tune something for just maybe 5-10,000 rupees and get 97, 96, or 98 also as percentage of accuracy? Why would I waste so much hardware, resources, computation to just achieve that 1% extra until and unless that 1% matters? Okay, so there might be many use cases, something like hospitals, medical use cases, lawyer or law use cases, where maybe important decision makings are involved. Maybe there I would say that rather not lose that even 1% of accuracy, let's boost it if it is needed. Okay, so that's the idea. That's one limitation that will come off, that these techniques will definitely reduce your resource requirement, but it will somewhere cut cost, okay, and that cost cutting will be available in your outputs. Your outputs will be little degraded as compared to the original models, right? So PEF demonstrates inferior performance compared to full fine-tuning models, but PEF optimizes the resource so much that it becomes overvalue for money. Okay, so that's the idea. I think we are able to capture it. Let us see if the window is open to doubts. If you people have any doubts still here, you can ask me. Okay, we are good to go. Can I quickly have a chat in the live that yes, we are good to go. Yes. So can you please tell when the coding will start? All right, then let's completely proceed to the coding part, which is so again complexity in method selection. We'll skip it. Let us jump to conclusions. I think conclusion is also delivered. Let us now start with the coding layer, and we will start in the next 5 minutes maximum. Let us just once go back and see. Maybe we are using llama 3.18 billion. Okay, so these are this blue, this whatever color is this. To me, it is light blue or green, whatever it is. Maybe a light blue. Okay, so this light blue stacks of layers are showing you that how different layers in an encoder decoder layers are. Okay, maybe a decoder layer. So just loading them, I showed you it takes up to 32 GB of memory, right? So we can apply adapters, which are like LoRa adapters, only to the target layers which we want. In our case, it is the activation or the attention layers, right? And you can see each low rank adapter is two small matrices, LoRa A and LoRa B. Okay, so even for an 8 billion model, you can realize that why using LoRa is beneficial. Okay, so if you have 8 billion parameters at 32 bits, it is 32 GB. Okay, so to keep the number of bits but to reduce the precision, okay, that's the idea where it comes in. So even if we reduce the precision to 8 bits, or even 4 bits, we can still retain all the weights but at a smaller size. Okay, so there is a variation in LoRa which is known as QLoRa. Okay, so this is one special technique of LoRa which is useful to further reduce the weight sizes. And how is it possible that suppose if I'm writing a number with 32-bit precisions like 6.12151, something like this, so after decimals, I'm reducing 32 float precisions to 16, and from 16 maybe to 8 or even to 4, or maybe to even go to 1. Okay, so again, what the original paper of QLoRa proposes is that even if we change the precision from 32-bit to 8-bit, it doesn't impact the performance of the model. In fact, this is where DeepSeek model came into picture, and trust me, DeepSeek definitely proved many of the American industries wrong, that maybe using 32-bit precision is not this optimal way. Okay, in fact, even if we drop the precision to 16-bit or 8-bit, the model is still as good as 32-bit precision would do. Surprisingly, okay, even 8-bit precision is working good, even just with a drop of 0.5 or 0.6% of accuracy. So, all right, now let us talk about certain essential hyperparameters which are involved in QLoRa. Okay, so first of all, the very first one is known as R, or the rank. How many dimensions in lower matrices do we need? Okay, so as you remember, I told you that LoRa A and LoRa B will have lower rank of matrix. So okay, rank of matrix is nothing but the concept of mathematics that you all know. So how to choose R? Okay, so the paper suggests, or the most common thumb rule is that start with 8, and that's the smallest. Even you can go for 4, but going to 4 maybe starts diminishing the accuracy to noticeable in aspects. Okay, you could go as low as 1, I don't mind. Okay, but 8 is a good size. Maybe you can go as high as 16. These are nothing but the rank of smaller matrices. What rank of matrices, what size of matrices we will create. This is a hyperparameter which is involved when we will be tuning LoRa. Okay, and the next is alpha. So remember, alpha is nothing but a multiplication hyperparameter. So it will just multiply your lower rank matrices in the dot product, right? You see how it will work is, so we have weight, okay. So let me just quickly give you this visualization, okay. Let me open up a whiteboard quickly, okay. All right. So suppose if we initially have W original, I'll call it W original, okay. And if you're going to change it, what will happen is the new weight will be W original plus W updated, okay. We will update the weight with the updation part, okay. So what will happen is inside this part for y is equals to W, which is the weight WX plus the bias term, any fine tuning will introduce W plus W update, okay, along with X plus B. So what we are doing over here is, first of all, to update this WU, we are using LoRa A and LoRa B, okay. So we are using this. And again, so where is R coming into picture? So R is coming into picture to decide the rank of what this matrices ranks would be, okay. And how is alpha coming into picture? So alpha is used to multiply them, okay. So alpha is a multiplication factor which will amplify them with so this thing will be multiplied with the W actually, okay. So alpha is the multiplication factor which comes into picture. It's or a scaling factor, and a thumb of rule is that you have to take its value twice as the value of R. So if you have taken R as 8, maybe you can take the alpha as 16. If you have taken R as 16, you can take alpha as 32 and so on, okay. But again, you can play around with these numbers when you fine tune, okay. Okay, so Tarun is asking, sir, if PEF techniques give us good accuracy, then there is no need for full fine tuning, even if we have enough resources. Yes. So, well, that is where I answered that if the big if question, okay, if that 1% matters to you, I give you certain examples, like maybe we are building use cases for hospitals or legal firms or somewhere where the decision making capacity is extremely critical. Only in these cases it will make sense. Apart from it, yes, it will never make sense to go for full fine tuning even though we have resources, because it won't make sense. It's an overkill, okay. So that's the idea, Tarun, because these fine tunings are really expensive. Okay, so now moving back. So the third is target modules. I told you how LoRa would work, or QLoRa is not different concept. QLoRa is just quantized LoRa. And what does quantization mean? Quantization means that we reduce the precision of the numbers, the way we are storing numbers. If you are into programming, you will know that there are different data types: integer, float, double, okay, like more precision to float. So it's nothing but the way in which these original American models work. They use 32-bit precision, like 8 point, there will be 32 decimals after the point, okay, and 16 would be so something like that, okay. You can take up the task. See, 4 bits are interpreted as a float, okay, not integer. So that's the idea. So with that being said, this dot precisions will be available, okay. And now target modules are what? Target modules are where do you want to target the adapters, where do you want to put these adapters in the actual model. So remember I told you we will be using attention layers, so we will target them, okay. So let us first, now before we start coding, let us understand that we will need Google Collab notebook, okay. So if you are new to Google Collab, you can just Google search Google Collab notebook. collab.research.google.com is where we want to go, okay. When you come here, you will say welcome to Collab, okay, and this will be a few different notebooks which are recent, but you can simply start with new notebook, okay. You can select a new notebook. Once you've selected new notebook, let me just quickly give you some fair idea of how the environment looks like. So on the Collab, this is how a new notebook will start. You can give a name to it, sample notebook. You can name it whatever, fine tuning LLM or something like that, okay. You can just close the release notes. This is where you will be writing code. Okay, so print, by default it works with Python. This is where you will write code. Okay, and it is very similar to your Jupyter notebook. It's a notebook basically, and this is how the code will run. It will be connecting to, and on the right you will see it is mentioning connected. Once it is connected, Python 3 Google Colab notebook, it has 12 GB RAM and 107 GB temporary storage connected to this instance. This is a free tier, and this is where you will write your code. Okay, on the left you will see there are 3-4 options. One is like the files. From the files you can upload some temporary files in this runtime. You can connect your Google Drive from here. Okay, you can mine Google Drive or upload files, which you can use the local storage. And then you will see there are secrets. So this is comparable to your .env. How in Python we have a .env file to store secret keys. So similarly, we can add secret keys over here. Maybe if you're using OpenAI, you can say OpenAI key and give the value. Okay, say a value, something like that. And maybe if you're using something else, then you can give network access to it. So this keys will be accessible by a notebook. Then these are different code snippets that you can take and certain find and replace. Okay, so this is about it. On the top you will see there is files from where you can download this as a Jupyter notebook, as a Python script, or you can print it as a PDF. You can upload or open new notebooks, edit, you can edit and do, and view, you can change the view a little bit. You can insert more code cells. You can also do it by clicking on the plus button right below this code over here. Okay, you can click on this plus button to add more code or text blocks. In the runtime, it is interesting. In the runtime, you'll be able to run all your cells, or run before, run after. And very important thing over here is how do you change runtime. Okay, change runtime type will explain you what do you want to run. Do you want to run R, Julia, or Python? See, these are the 3 different programming languages which are supported by Google Colab. Apart from here, you will realize what type of hardware accelerators do you want to use. Do you want to use a CPU machine, or do you want to use a GPU machine? We will need a T4 GPU, which is currently free of cost for us, but with some limitation. Higher performing GPUs like A100 and L4 are not available for free tiers. Okay, you can purchase some, you can say GPU resources, and you can use it. But for training the Gemma model, or for training any large language model, you will need to switch to the T4 instance. Remember, this is very crucial. I'll not be repeating it again tomorrow. So for all the people who got little sleepy throughout the presentation, wake up. This is your call. Remember what we have to do. You have to be familiar with using Google Gemini. You have to be familiar how you can change your runtime. Just go to runtime, change runtime, and it should be connecting to a GPU machine now. With this GPU machine, you will get a free 16 GB GPU, which can be used to train our small models. Now, while it is connecting, let me take you to yet another important place where it is mandatory for all of you to have an account on Hugging Face. So I think many of you are, if you're into AI, if you're into this session, you would already have a Hugging Face account. If not, just go to huggingface.co. This is the website's name, huggingface.co. Just go over here. You can click on sign up if you have not created an account. Let us confirm if you're human. Okay. Choose all the beds. Okay, 1, 2, 3, 4. Is this okay? Even as a human, I'm missing something. All right. Let's confirm you're a human. Choose all the hats. So 1, 2, 3, 4, 5. Confirm. If you have to join in, you can use any email ID. You can use any strong password right over here. Okay. Let me just once change it, because this is on a recorded screen now. Okay. So maybe I'll use a strong password. Okay. All right. So now once we have it, we have a strong password. Let me add this tab back. Let me see if you're able to. Yeah, you're able to see the screen, right? Okay. I'll click on next. And once you're clicking in, maybe you can give your name, okay, say llama 3.1, okay, and you can give in your full name. If you have Twitter account, GitHub account, or options, I've read terms and condition, and I'll create. Please match the format. No dash dot are required. Okay, so llama 3, I'll call it, and I'll create account, and then maybe you can choose an avatar. For now, you can. Okay, let me just create it. Sorry, I think something went wrong. Let me click on all the buckets first quickly. That's right. Yeah, nothing went wrong. I just simply skipped my display picture. Okay, so you will see llama 3 is the account which is created now. It doesn't have a display picture. And over here, what we will do is, so we have some free quota, like 0 GPU, we have 4 minutes of private storage, we have 4 minutes. But this is not something where I want you to focus on. I want you to focus on access tokens. Okay, you need to generate one. Trust me, people. When you are generating an access token, click on one. This will be really useful. But before that, check your email address to confirm the link. Let me just quickly check my Gmail quickly. Okay, I'll go to gmail.com. I'll go to this email ID. I'll click to verify the account, and your account has been verified. Okay, and I'll just reload this. Yes, my account has been verified. Now I'll have to create a user access token. I'll click on create a new token. So fine-grained tokens are useful when you have to select only particular type of requests that the token can work with. Okay, read tokens are read access only. Write tokens are something that are quickly available. These tokens have both read write and all your accesses to you and your organizations. So just generate this token. This token cannot be changed after creation. Remember it. Let's name it anything like fine tune llama collab. You can name something like this. You can create the token. As soon as you create it, so this is the value. Okay, you need to copy this, people. Trust me, isko copy karo kahin par and do not share it with anyone. The reason I am putting it on live screen because I will delete it just after its creation. Ye token bahut sensitive hai. You should never lose it, never share it. Okay, this token is something that can lead people to access this account. Okay, anyways, this is a dummy account that I've created, so it won't bother me. But I'm telling you, copy this and save it somewhere because वापस नहीं दिखेगा. Now I'll just click on delete this token. Okay, but this is how you will create a token. I hope the idea is pretty clear to you now. Now let us go on to our day one of fine tuning LLMs. Let me click on share. Where is the share notebook? Okay, I'll just try to download this notebook and give it to you in the links after the session. Okay, so see, there are certain tips that are mentioned over here. Okay, you can skip it for now. I'll take you through the journey. So first of all, what we will be doing is we will be installing few important libraries which are needed, like PyTorch and Torch Vision and Bits Bytes library transformers. Okay, we will be installing them. Okay. In fact, you can skip this part. I was getting some issue, which is why I installed it. Now, the reason why I'll not be running this notebook live and I'll give you as an assignment is because it takes time. Okay, even to download these things, it might take 4 or 5 minutes. So I'll just walk you through the notebook. Now, once you have done it, we will be importing all the important libraries like OS, math, okay, the torch, and you will realize this is where PEFT comes into picture. From PEFT, import LoRa config and PEFT model. Remember, from transformers, we need these things because these will help us load the models architecture. Okay, so if you realize, we simply installed these models, and this is where we installed PEFT. Okay, PEFTs and datasets, which will be useful to download our training dataset and work with the PEFT model. So once you have installed this, okay, now let us explain what our base model will be. So from where do I get base model? Look into it correctly, people. Let me go to Hugging Face. Okay, let me go to models, or I can even simply try to search over here. Say if I want to work with llama, I'll search for llama, and this is where I will see different models, 3 billion, 8 billion, and so on. Suppose if I want to work with a 3 billion model, uh, expand to view requests. Okay, this is where you'll have to scroll down and you will have to submit this. Remember, this is very crucial, that if at all you people want to fine tune a llama model, if at all you want to fine tune anything, you will have to first fill this form. Okay, fill this form, fill in your birth date, affiliation. You can give any company. Suppose if I work for Fractal Analytics, I can just put in something like that. Okay, and you can put a job description. It could be anything. You can select anything like a student researcher or AI researcher. Click this and click on submit. After doing this, so let me just do it once for you. Okay, I'll select some random values. So for an example, if we select any random value like over here, okay, maybe July 3, India, Fractal Analytics, AI researcher. When you click on submit, okay, your request to access this repository has been submitted and is waiting for review. It can take a day or two. Okay, if approved, you will get access to all 14 repositories, all of the metas, llama 3.2, 3.1, 3.3, and everything. You'll get access to it, right? If at all it's approved, which mostly will be approved. Okay, similarly, if you want to work with Gemma, you'll have to search Gemma over here, and suppose if you click on any Gemma model, okay, suppose if I want to work with say Gemma 2, okay, for an example, I can see Gemma 2 billion models. Let me click on Gemma 2 billion model. Okay, and over here, acknowledge license. What I'll have to do over here is I will have to authorize this. I'll have to fill in the form at Google. Okay, so I'll fill in the form at Google and I will run through the disclaimer. I accept the disclaimer and I'll accept this form. After accepting it, now I am licensed to use Google Gemma. Similarly, I have already filled the request for Llama. Llama will take some time, a day or two, to give you access, but Gemma 2 is now available readily. So you see right over here, there is copy model name to clipboard. You need to click on this. From here is where you will fill in your base model. Okay. So I hope people, you are okay till here. No doubt still here. We are running through our notebook. We installed the dependencies. We loaded them. Okay. And now we have a base model. And I'll quickly talk about what are the target modules. But if you go to a presentation, you realize the three essential hyperparameters, the R, alpha, and target module. And this is what we are defining over here. Our R as 32, we can keep it 16, no worries. We can keep it 32, no worries. It is all our choice. Okay, you can start off with these values. Now target modules are Q, K, V, and their orchestration. Okay, so you will remember these are the layers in attention module, query, key, value, if you remember, right? These are the layers in the attention module which are we are targeting. I told you, right? We will target attention layers only. Now HF token, this is where the game will change. I told you that how you can create an HF token. Okay, go to your GitHub account, not a GitHub, the Hugging Face account, access tokens, create a new token. Maybe I'll create a write token, create token. Okay, fine tune llama, create token, copy, done. Let me come over here in the secret keys. Let me add an HF token. Okay, and you will see that one HF token is added over here, and I have it. This is how you will have to set the HF token, people. Let me go back and delete this because it was recorded on live screen. Let me delete my tokens. Okay. Yes. So once you have successfully put secrets over here, you can just run this. Okay, and once you run it, I'm also printing you some of the initials of my token, and you will see that okay, I have loaded token correctly. Now, if at all you are going to run the next line, and if you get an error like you're trying to access a gated repository, fatal error, which means that you failed to get permission from the Google or any model you were planning to use. So if you're planning to use, say, Mistral, for an example, okay, Mistral small. So this doesn't use license, I think, so you can directly use them. Okay, let me try to use llama because for now I will not have permission to it. But anyways, I'm not running it. I'm just guiding you that error can come over here, and if that error comes, you already by now know what to do. You have to wait for the permission or switch to another model. The reason why we are doing it with Gemma is because getting permission for Gemma is very easy. A single form click and immediate access is granted. So immediately you'll be able to download these resources. So if you look carefully, we have to download more than 10 GB, 4.9 and 4.98, and then there are some small installations like 500 MB over here. Okay. So these are model weights. So weights are stored in tensor values. You can see we are loading safe tensors. So these are the actual weight of Gemma models. And now as soon as I click the memory footprint, you will realize that even a small tiny model, which is just 2 billions, like these are tiny models. We don't even call them small models, we call them tiny models, literally. So even something like a tiny model might need an 8 GB, 11 GB of free GPU. So if you are planning to run this even in your 70,000, 1 lakh rupees for gaming GPU, forget it, because even on 1.5 lakh budget, maybe there is no laptop which comes with more than 8 GB graphic card. Okay. So you will need at least a 2 lakh rupees decent laptop, or a 2 lakh rupees Mac, or even a 1.5 lakh rupees Mac to load this model's footprint, okay, in the memory. So with that being said, our other ways, you can load it on RAM. Loading on RAM is also possible, but that's useless. It's so small. Now, if we see what base model is, remember base model is equals to auto model. We are loading from Hugging Face, the transformer model. And this is the architecture over here. If you see, okay, how does the architecture of Gemma looks like? So Gemma model has embedding tokens coming right over here. Then there are layers. Okay, then there are decoder layers. In the decoder layer, there is attention layer. And you see the names Q, proj, and K, proj, and Y. They are not our decided parameter, the variable names right over here. These are the actual names in the model. So remember, target modules, whenever you're putting this array, you'll have to look at your model, how it looks like, okay? And what are the name of the layer? These are the name of the layers in the attention layer, okay? So these are it, okay? And there is again some more layers, like layers coming in over here, some linear layers, 10H activation, okay? And then a normalization layer, post attention normalization layer, feed forward layer, and a post feed forward normalization layer coming over here, and then a rotatory embedding layer with finally a linear layer for the output. So this is the complete architecture of the Gemma 2 billion model, and here we are targeting at the attention layers to adapt our LoRa. Okay, so this is where we will get it. Can we get read-only access to these notebooks? I'll provide you the complete notebook as a downloadable file, as a zip file. Okay, Nilesh. These will be available in the all-in-one document, but it's not right now available. I'll upload them in the all-in-one documents. For the people who are joining in tomorrow, they will get all the resources, okay? Not just this, I'll also give you the presentations that I've made it so that you can refer that also. So with this being said, remember I have mentioned restart your session over here. Now, if you want to load it in 8-bit precision, what you'll have to do is click on runtime, and you'll have to click on restart session, okay? Restarting session will completely eliminate your current cache, your current GPU load. So you'll have to go back and run imports once again and run base model once again. After running this, you can come back and then run this once again. Now, what is happening over here is this time we are loading the model in quantized format. Do you see this is where the bits and bytes config library will come into picture since that we installed, and we are saying load it in 8-bit equals to true, which now means that this model will be loaded in 8-bit precision only. So if you look at the previous print statement, which is memory footprint, this model took 10.5 GB, and just by quantizing it by using LoRa techniques, we are now only using 3.2 GB, and 3.2 GB is very easy. Even a 60,000 rupees laptop will have 4 GB graphic card at least, okay? But make sure it is not 1060 or something like that. It has to be CUDA compatible. So even as small as 2060 ka GPU hai, 70-80,000 ka budget hai, aram se 40-50 ka laptop aa jayega. I mean, that 40-50 laptop you can run even a little bit bigger models. Because 3.2 GB में आप 2 billion models fit कर रहे हो. So if you have 6 GB of memory, you can go for even for 11 or 13 billion models with quantized versions. And now score quantize कर दो, 4-bit पे कर दो. You can easily load even then 20 billion models in your smaller GPUs. Okay. So quickly, students, try to see what has changed in the architecture. एक बार quickly check करो. Let us see what people can bring in the chat के architecture में कहाँ पर कुछ change दिख रहा है. If you're able to see any change, let me know in the chats quickly. Well, if you're trying to struggle to see कहाँ पर change है, so actually there is no change. If you remember how LoRa works, LoRa will not change the architecture. वो कहीं पर कुछ भी weight को freeze, unfreeze, layer modifications नहीं करेगा. ये बिल्कुल वही architecture है जो यहाँ पर था. Only thing is we are adding adapters. That's it. And LoRa में adapters load करने के लिए ये जो architecture है same है. All weights are same, only their precision is less because they are quantized. Okay. So quantized config को we will load. Quantized config will be, we will load it in 4-bit. अब इस बार 4-bit में ट्राई करके देखते हैं. Then we will load the base model in 4-bit configuration, and if we load it, you will see कि अभी तो सिर्फ 2.19 GB ही चाहिए. That's all we need to load this model. So do you see एक 10 point something GB का model 2 point something पे आ गया, 80% reduction. I told you, right? आप at least 70% reduction कर दोगे by using LoRa, and then you can reduce it to 80% by using these models. Okay. So the idea of this notebook was to explain you how LoRa and QLoRa actually load the model. हम data sets को कैसे load करेंगे और कैसे work करेंगे. So this is a little bit about it, and well, कितने parameters हैं और size क्या है, you can see from this cell. Now let us talk about what data set we are using. So we are using Pricer data set. ये भी Hugging Face में मिल जाएगा. What you'll have to do is you'll have to search Pricer data, and you will see कि यहाँ पर these are the Pricer data models available. Deadshot, Adona, different people have loaded this data. आप कहीं से भी इसको use कर सकते हो. And from here you will see that it has 400,000 rows in training set. Test set में 2,000 rows हैं, and each of them have like how much AC compressor, repair kit, ऐसे एक text आएगा. Okay, you have a text like this, और model को इसमें से ना predict करना है इसका price. Okay, extract करना है, ये extraction का task है. मान लो हमारा project क्या है, so the project that we are doing, people over here, that will be extracting price from the given input text. Okay, so you can walk through this price here data. Okay, ये data set को check करो, you will realize that the output of the model is supposed to be to extract us this text values. So what we will be doing is starting in tomorrow's session, we will firstly load the base model. उस पर हमारा data set लगा के performance देखेंगे. Then we will write our own script to fine tune this model on this project, and then we will see how our fine-tuned model works on it. So this will be a really interesting project. Trust me, ये कोई छोटा मोटा project नहीं होगा. You can put this project on your resume. This is definitely a resume जिसमें आपका LoRa का training बहुत अच्छे से दिखेगा. You will be able to publish it कि hey, I have worked on LoRa. I understand how LoRa works. I understand what is R alpha target modules. But students, ये 3 day का bootcamp था. एक डेढ़ घंटे का. इन दिस वी कुड ओनली गिव यू हाई लेवल अंडरस्टैंडिंग ऑफ हाउ इट वर्क्स. मैथमेटिक्स कवर नहीं हुए हैं. दैट्स अ डिस्क्लेमर एंड एन एनकरेजमेंट के as a learner you should put more efforts, try to learn how this decomposition works, how matrices are broken down, and how these things are working in, right? Learn more about encoder decoder attention layers, learn around with mathematics around it, build a solid foundation, then you're good to go. So that's all for today's session. Unfortunately, I have a meeting starting in with some of my other commitments, so I'll have to drop off at 7:45. But yes, do not worry, for no confusions. You will get all the presentations, you will get all the notebooks, you will get all the notes. Everything will be provided to you when we start tomorrow's session. Okay, so thank you so much for joining in, people. I hope you really enjoyed learning how LoRa technique works or how PEF technique works, and you were able to understand the notebook with us. Thank you so much.